Alright, hello class. In this video we're going to be moving on to the next module of calculus, which is we're going to look at the introduction to the derivative. And the derivative kind of takes us all the way back to that motivating question, or at least that example of the motivating question of why we talk about limits in the first place. It allows us to deal with 0 over 0 cases, and 0 over 0 cases crop up in a really important application, and that comes through the derivative. And specifically in this case, it's what's known as the instantaneous rate of change. Okay, so this is a sort of advancement of the idea of the average rate of change. Okay, so essentially what we're going to be looking at is how we go from the average rate of change to the instantaneous rate of change, and we are going to do that essentially using limits. Okay, so if you remember, the average rate of change of f of x over the interval a to b is given by this formula here. I use this notation, the arc of f over a to b. That's just my own sort of notation there. But it's f of b minus f of a all over b minus a. This is essentially just calculating a slope across a function, right? Because up top here, this is just a delta f, or technically our delta y, over delta x over this particular interval, right? So it's essentially slapping a slope on top of f of x. Right, to give you an example what I mean by that, if we have, say, a graph of f that looks something like this, and let's say here's our a and here's our b. If we were to draw a line between f of a and f of b, or specifically the point a comma f of a and b comma f of b, let me try that again. Right, there we go. If we draw a line between these 2 points, the slope of this line is the average rate of change. Right? And this is actually kind of a hacky way to talk about the average rate of change. But it still works surprisingly well. Because it essentially gives you, your rate of change on average over the entire interval. So, for example, if our function looks something more like this, say it had a lot of increasing and decreasing and increasing, and it's oscillating, right? And here's our a back here, and here's our b. Well, if we were to just draw a line between these 2 points, okay, well, this gives us a really good idea of how the function changes on average, because based on this line, on average, our function f of x increases over a to b, right? It is slowly increasing. However, on a micro scale, we have increases and decreases, right? The function itself is going up and down. So while the average rate of change is a great way to talk about what's happening just on the macro scale, we actually want to start focusing on what's happening on the micro scale. Like, what's our rate of change at this point? Okay, we should be increasing here, but how about at this point? Or this point, or this point? Okay, so what we are going to do is take the average rate of change and analyze it on smaller and smaller and smaller intervals. Alright, so what we're going to do, like I said, is just take the average rate of change on smaller and smaller intervals. So for example, if our b that we're talking about is 1, we're going to consider the average rate of change for A's getting closer and closer to 1. So consider the average rate of change from 0.9 to 1, 0.99 to 1, 0.999 to 1, 0.9999 to 1, etc. Eventually, if you're talking, say, 0.999999999 to 1, right, your delta x is going to be something incredibly small. So you're talking about the average rate of change between almost 1 and 1. Okay? So if we start getting closer and closer and closer to this, we might actually start to see us getting closer and closer to an actual number. So if we were to do this with something like, let's do something simple, like x squared. Okay? Okay, so for the 0.9 to 1, the average rate of change for this first one would be f of 1 minus f of 0.9 all over 1 minus 0.9. Okay, so, right, so that's going to be 1 squared minus 0.9 squared all over 1 minus 0.9, which will be 0.1. Okay, so when we calculate this, okay, I got about 1.9. Okay, and then for the second one, we do this again. I'm going to get 1 squared minus 0.99 squared over 1 minus 0.99. So that's actually going to be over 0.01. Okay, so, all right, I ended up getting 1.99. All right, then we'll do it again. However, I imagine at this point you could probably guess that when we do the next step, we'll probably get 1.999. All right, which is what we do get. And so at each step, every time we get one extra, say 9, or one extra decimal place closer, we're going to add another 9 to our pattern here. So on this interval from 0.9999 to 1, we'll get 1.9999. Right? In this interval, we'll get 1.99999. And finally, this last one, right, the average rate of change will be 1 point all this many 9s. Okay? So, the takeaway here is as our A gets closer and closer to 1, okay, and this is from the left, the average rate of change seems to be getting closer and closer to 2. All right, and this is where the limit comes in. Right? This is just a limit. Because what we're essentially doing here is, imagine x is time, and we're looking at the average rate of change between this number and 1. So if x is like seconds, we're talking about the average rate of change over this many seconds, which is almost nothing. Okay, in fact, it's actually kind of fascinating that this works. Right? Because what we're essentially doing is saying that the instantaneous rate of change of f of x at x equals b is, essentially the limit is a goes to b of f of b minus f of a all over b minus a. Right? We're basically taking the average rate of change, right, over the interval a to b, and we're letting a go to b and get closer and closer and closer to b. And when we do that, we end up getting the instantaneous rate of change at b. Okay? It's actually kind of fascinating because what we're doing is we're taking the average rate of change from b to b. Okay? And that's essentially what we're doing. We're essentially calculating the average rate of change from B to B, which gives us the actual rate of change at B, right? However, we can't just plug B into the formula, right? We can't just calculate, say, f of B minus f of B over B minus B, because what we get is 0 over 0. However, we can take the limit. Okay, so if we go back to what we were doing before, where we were looking at, say, f of x equals x squared, and we wanted to find the instantaneous rate of change of x squared when b is equal to 1, we can instead just use the limit. Okay, so in other words, if we want to find the instantaneous rate of change of f of x at x equals 1, this is essentially letting b equal 1 and then calculating, okay, the limit as a goes to 1 of f of 1 minus f of a all over 1 minus a. All right, and we definitely cannot just plug the 1 in, because we get f of 1 minus f of 1 all over 1 minus 1. So this is always a 0 over 0 case. Okay, but if we just, plug these values in, we'll get the limit as a goes to 1 of 1 squared minus a squared all over 1 minus a. All right. So we'll get the limit as a goes to 1. This will simply just be 1 minus a squared all over 1 minus a. And imagine if this were an x. In fact, we can use x in this formula. We often do. If this were just an x, we would probably just factor and cancel this one, which is exactly what we're going to do. Okay, we're going to factor this as the difference of squares, so we'll get 1 plus a times 1 minus a all over 1 minus a. The 1 minus a's cancel, and then we're left with the limit as a goes to 1 of 1 plus a, and now we can just plug this in directly to get 1 plus 1, which is 2, which is what we actually discovered from that table. All right, now if we remember back to one of our earlier slides here, and we remember that the average rate of change gives us the slope of this line here. This is actually called a secant line. Okay, and as we let, say, A and B get closer and closer together, these secant lines get closer and closer together. Or sorry, the points we use to make them get closer and closer together, and we get what we sort of saw when we were looking at this with circles originally. We start to approach a tangent line. Okay, to just show you on a graph made with software here, here's a secant line. Okay, and I'm going to look at this as here's sort of my A and my B. Actually, could probably give those, here we go, there's A and then there's B. Okay, so as we let them get closer and closer together, we see that these secant lines start approaching this line that acts like the tangent line in the circle. Essentially what a tangent line is basically right here when we get extremely close to one another. Right, that's essentially what's happening here. Okay, we get closer and closer to this line here, which is the tangent line. And what the tangent line is doing is at any point, the tangent line is basically pointing in the direction that if you were traveling along this path, right, it is pointing in the direction you would be facing and traveling if you were walking along this path. It's essentially the instantaneous rate of change. So the secant lines, okay, end up being the average rate of change, whereas the tangent line is what they approach. Okay, so here we have from this side, and we can actually look at the secant lines from the other side as well. And so on both sides, okay, they are approaching this red line I've drawn, which is the tangent line. So the tangent line, a lot of people will define it as a line that only touches the graph once. That's true, but I like to think of it as just barely kisses the line. It basically lines up with the graph itself. Here's another important distinction about it. Okay, here's the tangent line. If we zoom in real close, okay, you'll start to see that eventually there's no difference between this tangent line and the graph itself. Okay, so what the tangent line is doing, it's basically telling you the rate of change as a slope on a really, really, really small scale. All right, so at A, this line does tell us exactly how the graph is increasing or decreasing. All right, so here we have the tangent line is positive, right? The slope is positive, the line is increasing, and that corresponds exactly to where the function is increasing. However, if we move over here, okay, at this point, this is where the function is decreasing. All right, and if we look at the the secant lines, as we get closer and closer, okay, we'll see that we're approaching this tangent line in red here, okay, which is a line that is has a negative slope. It's decreasing, and so at this point, okay, let me clean this up a little bit. At this point, we got a negative slope, and that corresponds to where the function is decreasing. Okay, and actually, if I sort of just focus on the tangent lines and start to move them around, okay, we can see that, so here, where the function is increasing, we're getting positive slopes. However, the slopes themselves are getting smaller and smaller as the rate of increase is lowering, right? And here, at some point it levels off and then becomes negative as the function decreases. And then sort of levels off again, and then the slope becomes positive as the function begins increasing again. Okay, so to kind of bring this all together, the average rate of change of f of x on the interval a to x is the slope of the corresponding secant line. And so the book often calls this m subscript sec, slope of the secant line. And that's just our average rate of change formula. We're just looking at it at the interval a to x here. Like I said, when we talk about the limit, we tend to want to put it in terms of x. And then the instantaneous rate of change of f of x at x equals a is the slope of the tangent line at a comma f of a. And that's going to be just the limit of the average rate of change. Okay, so we're basically taking those secant lines and shrinking them down on as small of an interval as we can. Okay, and that's going to give us that instantaneous rate of change. All right, and once we have the slope of that tangent line, okay, we have the slope and we have the point. It's going through the point A, comma, f of A. Since we're going to be finding the equation of the tangent line a lot in this class, the equation of that tangent line is going to be this. Okay, using the point slope form of the line, we're going to get y minus f of A is equal to m tan times x minus a, or y equals f of A plus m tan times x minus a. All right. Okay, so from here, let's look at an example, and then we'll talk about another way that another definition we have that we can deal with this. All right, let's take a look at this example. Let's say a cannonball is fired vertically from the ground with an initial velocity of 96 feet per second. And the position of the cannonball in feet above the ground at t seconds is given by this function here. S of t is equal to negative 16t squared plus 96t. This should be fairly familiar, I hope. This is basically your kinematics formula. Right? This is your gravity term here, negative 16t squared. That comes from the 32 feet per second squared acceleration of gravity. And then here is our initial velocity of 96. And if we had fired the cannon from, like, say 100 feet in the ground, we'd have like a plus 100 here. All right, so let's find the average rate of change of s of t on the interval 0 to 2. Okay, well, the average rate of change over 0 to 2, this is also often referred to as m sec for the slope of the secant line. Okay, but that's going to be s of 2 minus s of 0 all over 2 minus 0. All right, now you need to be very careful about how we do this. In this case, perhaps not. It might not be that huge of a deal, but we need to plug 2 into S and 0 into S. Now I know some students like to do these two things separately and then subtract them at this stage. That's fine. Okay, I'm just going to do it all at once though. So, and I'm going to put these in brackets. So I'm going to have negative 16 times 2 squared plus 96 times 2, then minus, when we plug in the 0, we'll get a 0, okay, because these guys are 0. And then that whole thing will be over 2. All right, and when we crank this guy out, I got 128 over 2, and that's going to be 64. Now the question is, 64 what? Okay. Well, remember, this is a fraction, right? This is delta S over delta T. So when we get down to here, the units are going to be in the units of S divided by the units of T. So this is actually 64 feet per second. Okay, this is an average velocity. Okay, in other words, this is telling us that the cannonball has an average velocity of 64 feet per second over the first 2 seconds of its life. However, keep in mind, this is just an average over the first 2 seconds. It's not the velocity it's always traveling at. All right, so big note here, this is not how the cannonball is always traveling, it's just an average. And we definitely know that for sure because its initial velocity, we're told, is 96 feet per second. So at t equals 0, the cannonball's velocity is 96. So at t equals 0, v is 96 feet per second. Okay? So that's what I mean when I say this is an average. It's just telling us sort of what's happening in the macro scale, okay, over this time period. All right, before we start looking at some instantaneous rates of change, let's find the average rate of change over 0 to 6 now. Okay, so the average rate of change over 0 to 6, that will be s of 6 minus s of 0 all over 6 minus 0. And we already found that s of 0 was 0, so now it's just a matter of finding the negative 16, 6 squared minus plus 96 times 6. Okay, all over 6. Okay, and when I crank this out, I got 0 over 6, which is 0 feet per second. That is kind of bizarre. However, if you think about this function here that we started with, all the way back up here, this is a parabola. Okay, and this has 2 t-intercepts. Okay, so when we graph this guy, it's going to look like this. At 0, it's 0, and at 6, it's 0. Okay, and if we draw the secant line between a point on the x-axis and another point on the x-axis, the slope of the secant line is going to be 0. Okay, but that's, that's not that helpful because we know that this cannonball does move. Okay, it goes up and then comes back down. But what this is saying is that on the entire lifespan of it, being shot up into the air and then coming back down and hitting the ground, its average rate of change is 0. Well, all that means is that the velocities on this side, right, cancel out the velocities on this side. Because on this side, they'll all be positive, and on this side, they'll all be negative. Okay, in fact, if you were to quickly do the average rate of change from 0 to 3 and 3 to 6, you'll find that, well, we already know that s of 0 is 0, and so it's really just s of 3 over 3. And s of 3 is, when you plug that in, going to be 144 over 3, which will be 48 feet per second. Okay, and if we, go through this again from 3 to 6, well, we already established that s of 6 is the one that's 0. So we'll get 0 minus s of 3 all over 3. So this will be negative 144 over 3, which is negative 48 feet per second. Okay? All right, so hopefully you're seeing some of the limitations of the average rate of change. It can give us information that is kind of helpful, but not all that useful. So now let's start looking at the instantaneous rate of change. All right, so let's find the instantaneous rate of change of s of t at t equals 1. So the instantaneous rate of change, which will also be called f tan, that is going to be the limit, as we can do t goes to 1 of, not f, of s of t minus s of 1 all over t minus 1. Okay, so this will be the limit as t goes to 1 of s of t. So really we're just rewriting this negative 16t squared plus 96t here, and then we are subtracting by s of 1. So s of 1 is plugging in 1 into both of these. So this will be negative 16 times 1 squared plus 96 times 1, all over t minus 1. Okay, now this is possibly going to feel kind of funky, but once we get through this, I'll show another way to do this, which actually, and sometimes is simpler, sometimes maybe not. Okay, but what we're going to do is let's simplify this. All right, so I'll get the limit as t goes to 1, negative 16t squared plus 96t, and then this comes out to be 80, so we'll have minus 80 all over t minus 1. Now, we're going to try and factor. So we'll factor the top. Now, the first thing we can do up top, it looks like we could take out a 16. And I'll go ahead and take out a negative 16. So I have a negative 16, then I'll be left with a t squared minus, all right, that'll be minus 6t, then plus 6, when we take 16 out of 80, we'll get 5. Okay. So now, it looks like this can factor because we want factors of 5 that will sum up to negative 6. So negative 5 and negative 1 will do that. So we'll get the limit as t goes to 1 of negative 16 times t minus 1 times t minus 5. All over t minus 1, and we get a cancellation there. All right, so we're going to get the limit as t goes to 1 of negative 16 times t minus 5, and so we get, now we can just plug the 1 in, negative 16 times 1 minus 5, so that will be negative 16 times negative 4. All right, which comes out to be 64 feet per second. Okay, so what this is at exactly 1 second, the cannonball is traveling at 64 feet per second. Okay, so in other words, this is the velocity of the cannonball at that exact second. That's what the instantaneous rate of change gives us. It's the instantaneous velocity of the cannonball at each particular second. Okay, now a couple problems with this. One, if now I want to find the instantaneous velocity at t equals 2 or 3 or 4, then we have to do all this work all over again. Okay, so that's one problem. The other problem is that this particular method can be kind of complicated if you can't see how it maybe factors at the end. So there is another way we can approach the instantaneous rate of change with what's called the difference quotient form of it, and that does yield a what's probably considered the most common form of the instantaneous rate of change. So let's give that formula, and then we'll talk about how we can maybe do this work once and then have a formula that we can employ as we go forward. Okay, so the instantaneous rate of change is also known as the derivative. So I'm going to start using that terminology now just because it's easier to say derivative than instantaneous rate of change every single time. All right, so the derivative of f of x at x equals a is, often we use this notation, f prime of a. Okay, and we'll talk about a little later why it is we use this particular notation, but it's f prime of a, or it's also df over, say, dx. This is another notation that we use, or a dy over dx, okay, at x equals a. And this notation is used to remind us that this is literally just a slope. It's literally a delta y over delta x, where the delta x is getting smaller and smaller. So this is essentially a delta y over delta x, where delta x goes to 0, and when that happens, it goes to a dy over dx. This is what's called Leibniz notation. So the two mathematicians known for developing calculus pretty much simultaneously are Isaac Newton and Leibniz. Now, Isaac Newton is known more for the development of calculus than Leibniz. However, Leibniz has the much better notation. He's more known for the notation that he developed. Okay, anyway, that's neither here nor there. The big thing is that the derivative at a, okay, is going to be the limit as x goes to a of f of x minus f of a all over x minus a. Okay, or the other way that we can define the derivative is in terms of h. So this is the limit as h goes to 0 of f of a plus h minus f of a all over h. So notice all we're doing here is, this is the same formula that we're just letting x be a plus h and then keeping a, because you'll have f of a plus h minus f of a all over a plus h minus a. And so all you're left with on the bottom here is h. And so, and then if we're letting x go to a, well, a plus h will go to a as h goes to 0. Right? So what this does is it turns it into a function of the length of the interval. So this ends up being the length, right? The length of the interval that's going to 0. Right? So that's what h is. So the nice thing about this form is usually when we mess with these, we don't have to do much factoring, but also they work out the same way. It's always a limit as h goes to 0. Always. Okay, we don't have to worry about what a is in this case. And it tends to be the more standard form of talking about the derivative. So I tend to use this one most often. I know as a formula it probably looks worse, but in practice it actually is maybe a bit nicer just because it follows this same pattern every single time. Okay, and what pattern is that? Well, let me show you a trick going back to the last example that we looked at. Okay, so the natural question is, what happens if we need to find the instantaneous rate at a lot of different values, right? Say at t equals 0 or 1 and 2 and 3, 4, 5, and 6, and maybe at 1.2, and maybe at 3.39, and so on and so forth. Do we have to do that work every single time? Well, no. Let me show you a little trick. I want to find the instantaneous rate of change at any particular a. And since we're using t, I'm instead going to just find the instantaneous rate of change at a general t, let's say. So our s prime of t, I'm going to use this one, the limit as h goes to 0, s of t plus h minus s of t all over h. And here's why I really like this form of the derivative. This is what's called the difference quotient form, is what happens next. Okay, so what we do is we plug t plus h into our formula. So we'll get negative 16 times t plus h all squared plus 96 times t plus h. All right, so here is the s of t plus h. Then we just subtract s of t. So that second part is just copying. I'm going to put s of t indirectly. So negative 16t squared plus 96t. I think I've gone right off the screen there. Okay. And then the denominator is just going to be h. Okay. So now we're just going to simplify this. And I know it looks bad right now. However, we're going to see a lot of stuff simplify here. Okay, so I know initially it maybe looks worse than what we were doing, but in a step or two it's going to look a lot better. All right, so I'm going to simplify this. This will be negative 16. We'll FOIL this on top to get t squared plus 2th plus h squared. Okay, then plus, we'll distribute that 96, so we'll get 96t plus 96h. Okay, and then we will distribute this negative sign. I forgot to write it up here, but this is s of t plus h, and this is just s of t. Okay, so we're going to get plus 16t squared, and then minus 96t, all over h. And we can see a lot of stuff canceling here. Maybe not a lot right now, but these 96t's right off the bat are going to cancel. And then once we distribute this negative 16, so let's do that in this next step, we're going to get negative 16t squared minus 32th minus 16h squared. Okay. Then here I'm just going to copy down what we have left, the 96h plus 16t squared all over h. Now we get some even more cancellations, right? This negative t squared and this this negative 16t squared and 16t squared cancel. And then we are left with negative 32th minus 16h squared plus 96h. Okay, now notice what's happened here. Everything that did not have an h canceled, and that's going to be what happens every single time. The thing without h cancels. Okay, then we can factor out the h to get negative 32t minus 16h plus 96, and then the h's cancel. Okay, and now we're left with negative 32t plus, minus 16h plus 96. And here, remember, we're taking the limit as h goes to 0, so this 16h goes to 0, so this whole thing is negative 32t plus 96. All right, so yes, that was a lot of work. However, we only had to do it once, because what we found is that s prime of t is negative 32t plus 96. All right, so now we can calculate some instantaneous rates of change or derivatives really quickly. Right, s prime is 0, that's going to be a negative 32 times 0 plus 96, so that's going to be 96 feet per second. Well, that makes sense because if we remember, that is the initial velocity of 96 feet per second. So that's what we should get for s prime of 0. Okay, s prime of 1, well, that would be negative 32 times 1 plus 96. So that's going to be, what, 64? Oh, that's what we found earlier. All right, when t is equal to 2, we get negative 32 times 2 plus 96. Okay, so that's going to be 32 feet per second. And then at s prime of 3, we're going to get negative 32 times 3 plus 96. Well, that's going to be a negative 96 plus 96, so that's 0 feet per second. So what's happening if you think about a projectile, right? Its height has a trajectory like this, right? So it moves along, and then at some point, right, its initial velocity fires it upwards, and then it slows down. Gravity starts to slow it down. At some point it stops and then starts dropping. And that's what we're going to see here at, say, 4. It's negative 32 times 4 plus 96. Well, that's going to be negative 32 feet per second. Right? So this is when the cannonball hits its maximum, and here's when the height starts decreasing. And this gives us the rate at each time interval. Right? So this is at t equals 0, t equals 1, t equals 2, t equals 3, t equals 4, etc. Okay, so at negative 32 times 5 plus 96, we'll end up with negative 64 feet per second. And at 6 seconds, that's when we hit the ground, we're going to be back at negative 96 feet per second. Now, it's not always going to be this nicely balanced based on, other things going on, but for this particular example, this is what we got. Okay. Now, some of you who may have seen calculus before know that this is still way more work than we will be doing for the rest of the semester. That is true. However, for right now, what these exercises are getting at is reminding you that a derivative isn't just, say, the power rule. It's not just a rule, it is a limit. It is a very special limit where we take the average rate of change and shrink it down over a tinier and tinier interval. Okay, so to basically close up this idea, I'll do an example where we find an equation of a tangent line, but basically the difference between the average rate of change and the instantaneous rate of change, I like to think of it in terms of driving your car. Right, the average rate of change, this is like talking about the entire trip. Right, so what do I mean by that? Like, for example, let's say I drove from Greensboro to Nashville at about 70 miles per hour. Right, that's just the gist. Right, when you're traveling, say on the interstate, even with cruise control, you're never really going to be traveling the entire trip at exactly 70 miles per hour. Right? This is more like on average because, yeah, at some point you get stuck in some traffic and you, say, are below 70 and you maybe at some point when you're speeding up, right, to pass somebody, you're maybe going 80 for just a minute or so and then you drop back down to 70. Okay, that's what the average rate of change is. It's basically talking about your entire trip, right? Over the 8 hours, I drove at about 70 miles per hour. Okay, the instantaneous rate of change is what speed are you driving at the very second that you look at your speedometer. Okay, so at that exact second, you look down at your speedometer and you see, oh, it's at exactly, let's say, 74 miles per hour. All right, and you're looking at it exactly 2:15 p.m. Okay, that's the difference. The average rate of change gives you the idea of the entire trip, while the instantaneous rate of change is what speed you're traveling at the moment, the exact second you look at the speedometer. And that can be exact. That tells you exactly what's happening at that exact second. All right, so for a final example here, quickly, let's find the equation of the line tangent to f of x equals x cubed plus 4x at x equals 1. So the formula for the tangent line, if we adjust sort of what we had before that was using mtan, right, the formula was f of a plus mtan times x minus a. Well, instead of mtan, we can actually use that f prime notation that we've established now. So we could say that this is f of a plus f prime of a times x minus a. And we know what a should be here. We're trying to find it at x equals 1. So specifically, it's going to be f of 1 plus f prime of 1 times x minus 1. Okay, so this part we don't really need to worry that much about. It's, say, finding these two. The f of 1 shouldn't be much of a problem. F of 1, that'll be 1 cubed plus 4 times 1, so that'll be 5. Okay, so our equation is going to be 5 plus f prime of 1 times x minus 1. Okay, the real work here is finding the f prime of 1. All right, so let's focus on finding that f prime of 1. So f prime of 1, that's going to be, we can use either of the limit definitions of the derivative. I'm going to use the h going to 0 one. Okay, so it will be f of 1 plus h minus f of 1 all over h. Okay, well, we already know what f of 1 is. Thankfully, we've plugged that in already. So really, it's just going to be f of 1 plus h that we need to worry about. So that's going to be 1 plus h cubed plus 4 times 1 plus h minus f of 1, which we already found to be 5, all over h. Okay, so when we FOIL this out, 1 plus h cubed is going to be 1 plus 3h plus 3h squared plus h cubed. Okay. Now, if you ever wondered why or how people get these so fast, look up Pascal's triangle and how it works with expanding binomials. Right? Really, if you just look up Pascal's triangle, I'll spend a little more time on that in another video, but for right now, I want to go ahead and move on. So anyway, then we'll distribute the 4 to get 4 plus 4h, and then we'll have minus 5. Okay, all over h. And again, I have a 1 plus 4 minus 5. So these all go away. And exactly as I promised before, we're only left with things with h's. We have a 3h plus a 4h, so that will become a 7h plus 3h squared plus h cubed. Okay, all over h. This will always happen when you use this method, and if it doesn't, you've done something wrong. Okay, so that means you need to check your work, because if all the non-h things don't cancel, something's wrong, right? Because you want to be able to factor out the h to get the 7 plus 3h plus h squared here, so the h in the denominator can cancel out, right? Because you can't plug that 0 in until you get rid of that h in the denominator. Right, so we're going to get 7 plus 3h plus h squared, and the h terms go to 0, and so we end up with 7. All right, and that's going to finish off our equation. Equation of our tangent line is going to be y equals 5 plus 7 times x minus 1. And we could, simplify this as 5 plus 7x minus 7 to give us, that will be 7x minus 2. Okay, so there is the equation of our tangent line. All right, if we look at the graph, here's the graph of our function. Okay, so here's the function, here's the point 1, comma 5, and here's the tangent line going through it, okay, that we just found. All right, so that should definitely be enough to get you rolling on the homework for this section, and we will come back in the next lesson to talk about the derivative as a function, right? And so you may have already seen some of that already when we did this in general with t, and that's the basic idea, and that's going to be our first step into simplifying this and making things nicer for ourselves. All right, I'll talk to you then. Cheers.